If I gave you a flask with a chiral molecule in it, how would you know if the flask was the pure S enantiomer? You can't see the difference between the R and the S version. You can't smell it, but it can be measured. And that is where optical rotation comes in. Hey there, ninjas. This video will serve as an overview of optical rotation and polarimetry. We'll talk about what optical rotation actually is, how a polarimeter works, why we need a separate specific rotation. I'll tell you what the instrument is measuring, and why we can't trust the number that we read on the display. That overview will get us pretty far. So let's go back to the problem that we're trying to solve. If I give you a flask with a chiral molecule in it, how do you know it's a pure enantiomer? How can you tell if it's a mixture of R and S? And how could you tell what the ratio of the R to S isomer actually is? We need some way to measure chirality experimentally, and that is what optical rotation does. Optical rotation, as the name suggests, is optical. It depends on light. To understand optical rotation and polarimetry, we need a very simplified idea of light. You have probably been told before to think of light as a wave, and that wave can oscillate in different directions. And a normal, typical light source gives off light that is oscillating in every possible direction. We call this kind of light unpolarized light. In a polarimeter, however, we take that unpolarized light and first pass it through a polarizing filter. The polarizing filter blocks all planes of light except one. After the filter, the light is oscillating in a single plane. We call this plane-polarized light. And now for the key idea that explains what's happening inside a polarimeter. When plane-polarized light passes through a solution of a chiral molecule, each photon of light may hit one molecule of the chiral molecule. And when it does so, that plane of polarization gets rotated just slightly. The beam of light doesn't get deflected. It's the orientation of the plane of oscillation that gets rotated just slightly. And this happens a little bit at a time every time the photon hits a chiral molecule. So over the full length of the sample, that wave gets gradually rotated. And at the end of the polarimeter is another polarizing filter. After the beam of light has been rotated, there's only one orientation of that final polarizing filter that will let that light pass through and reach the detector. And we can measure how far we had to rotate that final filter and in which direction, and that gives us the observed rotation for a sample. What we might see on the display of a polarimeter is that rotation number. The number on the display tells us how far that final polarizing filter had to rotate in order to detect the light, and in which direction. So let's say we get a measurement of positive 20.53 degrees. That number tells us that the plane of polarization rotated 20.53 degrees in the positive clockwise direction. We could have gotten a negative number that would be rotating the light in the counterclockwise direction. But here's the problem. That number is basically useless. Let me recap what we saw in how the polarimeter works. Whatever light source we choose emits waves of light in every possible orientation. That unpolarized light passes through a polarizing filter and creates plane polarized light, where all of the light is oscillating in the same plane. As that plane polarized light passes through a solution of a chiral molecule, it interacts with that chiral molecule and slowly gets rotated as it makes its way through the path of the sample. And at the end, we rotate the final polarizing filter such that the light passes through, reaches the detector, and that gives us the number we see on the display. The problem is there are actually 4 dependent variables in this system. 4 variables that, if changed slightly for the same molecule, would give us a completely different reading on the display. Before I tell you what they are, pause the video, see if you can look through the schematic and find some of those dependent variables. For the optical rotation in a polarimeter, the observed rotation we see on the display is dependent on 4 things. One of them is the temperature at which the experiment is run. Changing the temperature will change the observed rotation. Another dependent variable is the wavelength of light that we choose to use in our polarimeter. Even for the same chiral molecule, different wavelengths of light would be rotated slightly differently. And the 2 variables that I think are most intuitive in this diagram are the sample concentration and the path length. Every time the photon hits a molecule, it gets rotated slightly. So for a higher concentration, the light is going to hit more molecules and get rotated more as it goes through the path. Similarly, as we extend the path length, the light will hit more molecules throughout the path length and change the observed rotation. If you were to take the same molecule and change any of these 4 variables, you would get a different observed rotation on the display of your instrument, which means without accounting for these variables, we can't compare numbers between experiments or between labs, even for the same molecule. So what do we do about it? Nothing. That's the end of the video. I'm just kidding. Of course there's something we can do about it. We introduce a new term, the specific rotation. different from the observed rotation. The specific rotation is a standardized value for the same molecule across all instruments. We start by standardizing the temperature and the wavelength. By convention, we always run the experiment at room temperature, and we always record that temperature in our reported specific rotation. Furthermore, we always use the same light source in all of our polarimeters. By convention, we use a sodium lamp and the sodium D line at 589 nanometers. That specific light, with a wavelength of 589 nanometers, is historically very easy to produce with sodium lamps and very bright. With those two values standardized and part of the way we report specific rotation, we can correct for the concentration and the path length. The calculation for specific rotation is to take the observed rotation from the display of the instrument and divide by the concentration and the path length. By correcting for the concentration and the path length, we get a standardized uniform value that we can trust between experiments and between labs around the world. The one thing that's always bothered me about specific rotation is how we standardize the concentration and the path length. I wasn't privy to these conversations and decisions, but we report concentration in grams of sample per 100 milliliters of solvent, not molarity or any other standard measure of concentration. The concentration specifically must be in the units of grams of sample per 100 milliliters of solvent. And the path length isn't much better. We report the path length in decimeters, not meters or centimeters or millimeters, decimeters. And now we've done something important. Instead of a messy experimental observed number, we now have a standard value for every chiral molecule. We can say things like S-alanine has a specific rotation of positive 14.5 degrees. When you run the polarimetry experiment at standard temperature using the sodium D line, once you correct for the concentration and the path length, every sample of S-alanine should give you a specific rotation of positive 14.5 degrees. Plane-polarized light should be rotated 14.5 degrees in the clockwise direction. Let me take a moment here and clear up one of the most common misconceptions about specific rotation. There is no correlation between the R and S label of a chiral molecule and the positive or negative specific rotation. It is not true. Every S molecule does not automatically have a positive specific rotation. In fact, if I change alanine just slightly by adding an extra phenyl group, we get S-phenylalanine, which has a specific rotation of negative 34 degrees. It's still an S molecule, but now the plane polarized light gets rotated 34 degrees in the counterclockwise direction. That's fine, there's nothing wrong with that. We just need to say out loud that R and S has no relation to positive or negative specific rotation values. The R and S label is a human construct you determine by applying the SIP rules. The specific rotation is an experimental value determined by physics. There is no way to predict the specific rotation just by looking at the structure. Not the direction of rotation and not the magnitude of rotation. One more important case to mention is achiral molecules, molecules without any stereocenters. If a molecule is achiral, it does not interact with plane polarized light in a directional way. So by definition, the specific rotation of an achiral molecule will always be zero. Finally, enantiomers have specific rotations that are equal in magnitude but opposite in sign. Hopefully that makes a little intuitive sense. If S-alanine rotates plane polarized light 14.5 degrees in the positive clockwise direction, the opposite enantiomer, R-alanine, rotates plane polarized light 14.5 degrees in the negative counterclockwise direction. One last case we have to address is mesomolecule. Recall that mesomolecules, yes, have an internal plane of symmetry, and yes, have a mirror image that is superimposable on the original. Because of that, mesomolecules, even though they have stereocenters, are achiral. And as an achiral molecule, it does not directionally interact with plane polarized light. So be careful with mesomolecules. Like every other achiral molecule, they will have a specific rotation of zero. With the polarimeter and specific rotation, we can identify compounds. We can compare results across labs. And very importantly, we can use optical rotation to start to assess purity. Because here's the big question that comes next. What if the sample that I put in the polarimeter is not one pure enantiomer? What if my sample is 70% of the S enantiomer and 30% of the R enantiomer? How will that affect the observed rotation in the polarimeter? Given an observed rotation, what does that tell me about the mixture of enantiomers in my sample? And that's exactly the subject of the next video. I'll see you in the next video, ninjas.
Thanks for watching. The best way you can support this channel is to let your friends know about these videos, especially ones who go to different schools. Help spread the word around the country. As always, don't forget to like and subscribe.